Okay, so we're looking at Pearson 12 in the review 1.3. A few people had some issues with questions 8, 9 and 10, and they all relate to reading off a graph. And I've had a quick skim of the book and it's in there a little bit, but there's just something about the questions that I thought I'll point out first. On the left hand side of the book you've got this graph here, and this is the one that it wants you to use for question 8. But if you look at the other graph that's on that in the book right next to it, it looks like that. Now, the shape of the graphs is exactly the same, and that's pretty obvious. And the axis on the x-axis is fine, it's the same. But on the y-axis, you can see that this one here is force, and this one here is gravitational strength, gravitational field strength. Now, the only difference between force and gravitational field strength is that force is measured in newtons, and gravitational field strength is newtons per kilogram. So, gravitational field strength is acceleration, and F equals ma. So, your acceleration is just going to be F on m, whereas this one here is just F. So, this graph and this graph are actually exactly the same. So this is given the force for 1 kilogram, and this is giving the acceleration, which is the force per unit kilogram. So I don't know why they've done it this way, but at the end of the day, no matter which graph you use, you'll get, we should get the same results. I've chosen to use this graph simply because it has more grids on it, which means that if I was going to spend a lot of time on it, I'd probably get a more precise result from this one. So this is what I'll be using to answer the questions. Okay, so with question 8, all right, a meteor of mass 1 kilogram is speeding towards the Earth. Now remember, this graph that I'm using is the acceleration, which is the force per kilogram. So I can, whatever this is in acceleration terms, I can say is the actual force. When the meteor is at a distance of 9.5 times 10 to the 6 meters from the center of the planet, its speed is 4 kilometers a second. So the first question is pretty simple. It just says determine the kinetic energy of the meteor when it is 9.5 times 10 to the 6 meters from the center of the Earth. So that's a pretty straightforward question of half mv squared. In this case, your v is going to be, so m is 1, 4,000, because it's 4 kilometers per second squared. And when you chuck that into your calculator, well, I got 8 times 10 to the 6 joules. For part B, it's asking to calculate the increase in kinetic energy of the meteor as it moves from a distance. 9.5 10 to the 6 meters to a point that is 6.5 times 10 to the 6 meters a second. So looking at the graph, we are now getting to a point that is 9.5, so we are here. Oops, sorry, we are here. And we're going to 6.5, which is up here. So we want to determine the kinetic energy when it travels from here, falling down to there. And all of this, the key to solving this is understanding that this here is the work, or the change in energy. So you know that work is equal to the force times displacement. This here is how much the asteroid has displaced, and that work is being done by the gravitational field. So here, if you have a graph of gravitational field strength, or in this case the force for 1 kilogram multiplied by the distance, you now have force multiplied by the distance, and you'll end up getting work, which is why the area underneath this graph is the work. So that's the key, is to figure out what the area under the graph is. So I'm going to try and estimate it, but very quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. Oops, sorry, 38. I was deliberately trying to land on 38 because that's what I got when I did this previously. The book is also consistent with 38, but if you get a little bit above or a little bit below, it's not terrible. So we have 38 squares. Now, how much is each square worth? across here, we can see that square there, that part of the square is 0.5 times 10 to the 6. And one part up is just 1 times 1. So what we should end up with is 19 times 10 to the 6, or 1.9 times 10 to the 7 joules. Alright. So let's have a look at the last question now. How fast is the meteor travelling when it is 6.5 times 10 to the 6 meters from the center of the Earth? Alright, so this here represents the work done, or the change in energy, and that energy is going from potential energy at the top as it's falling. It now comes over here, and it ends up being all turning into kinetic energy. So this here is your change in kinetic energy, I suppose. So the final kinetic energy at this point, I guess I could just say here 6.5. It's going to be equal to your original EK plus your change in EK, which is going to be equal to 8 times 10 to the 6 plus, I'm just going to use this number here, 19 times 10 to the 6, and that's going to be equal to 27 times 10 to the 6, which is 2.7 times 10 to the 7 joules, and there's your answer. So you then go and you want to get the speed out of that, and I'm running out of space, so let me write that. Let me get another piece of paper. Okay, so moving on from here, you've got your energy value. EK is equal to 2.7 times 10 to the 7 joules. That's equal to half mv squared. So that means your V is going to be the square root of 2.7 times 10 to the 7 times 2 over 1. So in this case, what we should end up with is 7348 meters per second in your calculator, or you can go 7.35 times 10 to the 3 meters per second, or as they have in the book, 7.35 kilometers per second. And there's your answer there. Alright, so now let's move on to question 9. We're looking at a communication satellite. It's given a mass now, so I'm still using this, except whatever value I get here is for 1 kilogram, so I just multiply that by 240 when I get to the end of the result. So it's launched from a space shuttle. It's in orbit 600 kilometers above the Earth's surface. So that's the key here. So first I need to work out what the distance is. So the distance that we're looking at is going to be the altitude plus the radius of the Earth. So in this case, we have 600 kilometers plus the radius of the Earth. In your data sheet, I get 6.38 times 10 to the 6. And when I do that, I get 6.98 times 10 to the 6 meters, which, let's just go with 7 times 10 to the power of 6. If you didn't get a number that corresponds to the graph, you're immediately realizing, okay, I must have made a mistake here. So let's go back to that question. It travels directly away, so we're going away this time, so this time we're launching something and we're giving it enough kinetic energy so it can be converted into potential energy. So it starts off at 7, so it starts here, and we're launching it by giving it a nice burst of kinetic energy. Now it's saying it goes to, where are we, sorry, 8,000 kilometers, or here. Okay, so we are now launching it this way and we're giving it kinetic energy, and as you'd expect, the question's asking here, use the graph to estimate the kinetic energy that this satellite was launched with. So let's bring it back down to here. We want to work out what the area under the graph is, because that is the work done to get the satellite from here to here, or from a low orbit to a higher orbit. So we just count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I've got 14 squares. And each square is worth, like in the previous question, 0.5 times 10 to the 6. And that's going to be equal to 7 times 10 to the power of 6. Now that is still joules per kilogram. Right? So now if we want to get that in raw energy values, we just multiply that. I should put EK. 10 to the 6 times the mass, which was 240 kilograms. And the answer I've got for that one is 1.68 times 10 to the power of 9 joules. There you go. Alright, last question, question 10. So now we have another mass of 20,000 kilograms. It's in a circular orbit at an altitude of 600 kilometers. So from the previous question, we've already done 600 kilometers here. So we know the altitude is going to be 7. So we're starting here at 7. Anyway, keep reading. The satellite has moved to a new stable orbit with an altitude of 2,600 kilometers. So we need to figure out another distance. So there's a radius of the Earth plus the altitude plus 260 kilometers, was it? No, 2,600, 0, 0, 0. And the number that I got around there was 9 times 10 to the 6. So we're going to here. So we have a satellite sitting at a low Earth orbit, and we are now kicking it up to 9 times 10 to the 6 meters. So the question, it's interesting, right? Because it's pretty much the same question as up here. You have a satellite here, you've moved it up here. What is the increase in gravitational potential energy? And that's given to it using, if it's launched, say, kinetic energy. So we just want to work out that change in energy. So it's almost the exact same question. Come down here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. What are we at? 24, 25, 26. So we've got 26. So we have 26 squares. Multiply that by 0.5 times 10 to the 6. Because that's what each square is worth. And that's going to be equal to 13 times 10 to the 6 joules. Remember, that's per kilogram. So to get the gain in, so the work in this case is going to be equal to the gain in potential energy, which is just going to be equal to what was the mass? Remember here, 20 ton, so 20,000 times 13 times 10 to the 6. And in the calculator you should end up getting something like 26 times 10 to the 11 joules. There we go. Whoops, I mean 2.6 times 10 to the 11 joules.